Hello, everyone. I'm Andrew Hockman.
Hello, everybody. My name is Hersh Patel.
I wrote all the Python code from scratch for this project, and I don't have time to go over every single bit in 2 minutes, but I'll try my best. So we have a base class that defines a gradient descent function, which essentially is this loop where we continuously iterate x and we store our history. This iterate function is the only part of this code that is different between the optimizers. So each optimizer inherits from the base class and defines its own iterate function. And then they'll also save anything they need to store for that iterate. So alpha will store m and v and k to define its own iterate function. Um, Now, from the main code, we start off by creating the functions. Wait, where are we? Create the functions. I used SymPy, so the gradients are calculated using the SymPy methods. I define all the starting points for the functions, all the alphas for the optimizers, as well as a range of alphas to try when we call this function. So very hyperparameters will go through every. This is the most complicated function by far. It goes through every single optimizer and every single function and every single initial point, and then it calculates the average iteration count for every alpha across all the functions and initial points, and the average completion time, and it saves plots of those, which are used in the report. Calc statistics is called that, and it will find the average number of iterations for the best alphas, as well as standard deviation and final function values. So we run the very hyperparams function, and then report variations is called here, and it will fill out the 108 different combinations of variations of functions and initial points. And then finally, we have a function called a function that plots. So this will you give it a list of initial points, and it calculates all of them, and it plots arrows to represent the gradient descent paths over top of the contours.
This is a summary and discussions about our findings. We noticed how much the results were dependent on where we started. When we looked at the convex bowl, it really did not matter where we chose to start because in any case, we ended at the point 00. This was not the case for the Rosenbrock and cosine bump. A good start location meant the optimizer could get to the global minimum, while a bad one often left it stuck in a local minima. Alpha was a big factor when looking at vanilla. Alpha basically decided whether the optimizer worked at all. If it was too big, the optimizer diverged, but if it was too small, it crawled along so slowly that it took thousands of steps to get anywhere. When we looked at the Rosenbrock function, vanilla gradient descent was f of x blows up towards infinity when the step size is too large. With small alphas, it just zigzagged endlessly through the valley without making real progress. It was eye-opening how poorly it handled the function compared to the other methods. We believe Newton's method generally worked well. We thought it converged in a handful of steps on the majority of the problems. It was impressive. On cosine bumps, the issue was that it sometimes stopped too early. Instead of finding the global minima, it would settle in one of the nearby and stay there. In our view, Atom was most the most balanced optimizer out of all. It handled the convex bowl just fine, did way better than gradient descent on Rosenbrock, and on cosine bumps it was usually able to escape the smaller dips and find minima.
Okay. Uh, So some of the most challenging and rewarding aspects of the project were one, planning out the code was fun and challenging. Trying to figure out the best way to lay it out. Ended up going with the inheritance structure. We found visualizing the contour plots to be very nice because it allows us to see where we're getting stuck in local minima and where we're escaping them. Actually coding things ourselves or helped us understand the math better. And looking through all the combinations of initial points and functions and optimizers was very rewarding as it allowed us to easily compare and contrast different optimizers.